Hi everyone, thanks for staying so late. Everyone's tired, including myself, but I'll try to make sense. Okay, so today I'll try to focus on our benchmarking protocol for graph planning algorithms that we introduced 5 years ago with my colleagues from University of Birmingham, DLR, Oregon State University, Yale. This is a little bit of an old work, but I would like to tell you about our thought processes and possible extensions at the end. So, okay, so there has been a lot of graph planning algorithms proposed over the decades, and there are still new ones coming. And let me see if this moves. And it's important to be able to compare them in a fair way, in a reliable and consistent manner. For this, we define a structured, repeatable process. We focus on different types of objects, success metrics, and way to evaluate robustness. I also want to especially emphasize the importance of trying things on real world, because no matter how hard you try to replicate what you plan in simulation in real world, things will fail at times. Okay, the challenges are that mainly diverse hardware. Everyone has different hardware, different embodiment, different environments. Algorithms vary a lot. They have different assumptions, different prior information. Reproducibility is always an issue, especially if you're dealing with deformable articulated objects or random clusters of objects. And it's quite difficult to untangle the whole system, because oftentimes the perception is quite intertwined in the planning algorithms as well. So how do you actually evaluate the real performance of the graph planner, rather than as opposed to perhaps it's relying on a pose estimator, so you don't want the pose estimator to influence the actual performance of the graph planner and things like that. So we want to compare the performance of different algorithms, and we want to define repeatable conditions in terms of objects, their placements, and we want to use a success criteria to quantify the quality of the performance. So we define some environment description and some systematic way of placing objects, and ways to quantify grasp success. So we focus on single objects and cluttered scenes, but the cluttered scene part is a little bit too primitive, and I will mention some work that actually improved cluttered scenes, of benchmarking cluttered scenes. So let's see. The way we define the workspace is as follows. So we want to facilitate generality and easy workspace construction. So we thought that it would be good to construct your workspace like this. Whatever arm you have, you point the tool center point or the end effector in this position, in this 1990 configuration, and where the tool center point points would become the center of your workspace, and you imagine a circular area around it with a certain radius, and you place your objects in this circular workspace. So the origin would be the initial position, and then we have front, right, and left of the origin, and for these positions, we also rotate the object. I'll show you object placement in a bit. So this is how we define the workspace, and we thought quite a bit about this to make sure that any robot can be placed and fit into this workspace. We are relying on YCB object sets because I think these are adopted well by the community. There's various objects in this: food items, kitchen items, tools, shape items, and we picked a subset of these objects in varying complexity. So really primitive shapes, a little bit more complicated shapes, a little bit irregularity, and increasing complexity, and finally some deformable or articulated object at the end. So 4 types of objects. And this is how we start. We start putting the object in the origin and then move it to the front, right, left, and then mirror. Also consider the rotated mirrored poses, because this is this is an asymmetrical object. So this is how you systematically move the object within the defined workspace. And since you are dealing with an asymmetric object, you can also consider mirrored cases. So you have in total 12 configurations. And we also have two discrete cases, objects, two discrete stable initial poses. Objects can be standing or lying. So this would be another initial state of the object. So once we place the object, we run the grasp planner, we execute the best grasp, which is basically the grasp with the maximum likelihood that your grasp planner finds. And we repeat this process n times. Hand control directly has an effect on the grasp success. And it's a little bit difficult to define a standard on hand control, because it depends on the embodiment, and everyone might have a different hand. Some two-finger hands, some maybe have a multi-finger hand. A common easy way to control a given hand would be to fully open it, pre-shape it according to our algorithm, then close every joint with equal speeds until reaching a steady state, or fully closed in case you lose the object and fail. So this would be how to execute the grasps. Then to verify robustness, we have a set of tests. You first need to lift it at a certain height, with a certain speed, then rotate it at this position, then a test. Basically, robot shakes the object with a specific amplitude in a sinusoidal pattern for a certain amount of time. These are all parameters that can be adapted. And the result is basically the average success rate of all the trials. And the test is stopped if you lose the object, and the shaking test is run after rotating. So if you fail rotation, you don't need to shake. And we define a number of failure cases. For example, if you lose the object, if the object slips away while reaching to grasp, or while lifting, or rotation test fails, shaking fails, or your grasp planner doesn't find any hypothesis, etc. And we provide a format of the formats to summarize the results. You record the object name, stable pose, was it standing or lying, how many trials did you run, the ID of the grasp that was selected, the total number of grasps, how much time it took to generate grasps, the binary success result of lifting, rotation, on rotational shaking tests. That's for single object grasping, or in case of clutters, similar, but maybe the difference would be the pickup order. So basically, we record success rates, robustness, perturbations, computation time, and number of grasps attempted. Here are some examples of the benchmarking protocol applied on a single object case scenario, cluttered scenario. And when we are dealing with clutter, we simply just put objects in a tray and then randomly place them within the circular workspace. We do experiments. We can also do experiments on a simulation. In this case, we run an open rave simulator. And here's an example of the robustness evaluation tests on a cluttered set of objects. So lifts, rotates, then shakes, and then we record the results. Okay, you can fill the table given a grasp planner. There we have some examples you can download and have a look. And we also have the summary of the assessment protocol and benchmarking protocol online. And in summary, this was our first attempt to evaluate different grasp planning algorithms, defining workspace, object choices, placements, grasp execution, and scoring. And of course, there are a lot of ways to extend this. We can add obstacles, more detailed instructions on how to set up repeatable piles of objects. automating some of these steps, increased degrees of difficulty in terms of picking order or additional task constraints. We can say, for example, I only want grasp that would afford pouring task, things like that. Adding more stability checks, more levels of difficulty for robustness tests. For example, linearly increasing or decreasing the acceleration in each cycle. We can include more complex tasks, tool use, in-hand manipulation, etc. And of course, support deformable or dynamic object grasping. And especially Maximo Roa's group did a lot of, I think they have a nice benchmarking protocol on it, at least for the cluttered scenes. So, thank you.
Questions for Yasemin? We had several mentions of this protocol earlier on. This is one we use in our lab quite frequently.
Oh, really? Nice to know.
I wanted to ask if are you familiar with this might have been the one out of Maximo's lab. Cluttered environment.
Yeah, I think so. That's the one. I think that's the one I was referring to.
That's one that utilizes at least the ordered picking, you kind of break down.
Yeah, but when we were writing this paper, there wasn't a lot of those benchmarking.
Oh yeah, this one.
Yeah, exactly. Maybe they came about the same time or a bit later. So because he was also an author in this paper.
Okay. Probably one of the extensions.
Yeah, exactly.
So one of the things we've been talking about a lot here is the difference between evaluating, say, a component of a pipeline, like a craftsman, versus, the top, what they're talking about, for example, on policies. Is there any work in your lab or that you've been involved with that goes beyond the, say, a grass planning module, but looking at like a full end-to-end?
We haven't looked into it, but yeah, that's definitely worthwhile looking into. And this is what I was saying as well. So, many old grass planners relied on pose estimation, right? And if the pose estimation was bad, you wouldn't expect good result. So it's important to be able to disentangle and separate them. But we haven't looked into how to do that yet. Yeah.
It's been a hot topic discussion.
I was going to push back a little bit on that last statement. It's important to be able to disentangle. Yes. It is important for grass planners to be able to accept noisy inputs. So you need to measure both, I think.
Yeah.
So since then, as you said, there are many new grasping planners, most of them data-driven. Would this change, however, the benchmarking process for grasping, you think?
We want it to be independent of the nature of the planning algorithm. Of course, that's what we want, but sometimes it might be difficult. But at least this one is generic enough, though it's quite manual. There is a lot of things here that should be automated because no one wants to place things manually. Maybe resetting software should be there. But yeah, ideally it should be independent of the nature of the planner.
Unless we get into what we said before, the more purposeful grasping, if you grasp with the intention to do something that perhaps you need to evaluate how you think it serves the
Can you go back to your extensions slide? Because you had mentioned if you were grasping more complex tasks, so for tool use, you have to grasp it in an orientation that is valid for whatever the next step would be.
And many people have developed now language conditioned grasping, right? Pick the rose from the stem. So it's a specification of where you grasp.
Yeah, exactly. I just want to show you some other slide from the other presentation. So
You might need to change what you're sharing.
yeah, exactly. Okay. So in this, exactly, task-oriented or functional grasping, right? So if you want to hand over, you need to leave enough room. If you want to pour, you should be able to rotate it, etc. Right? So this kind of requirements could be added. But it's not super deterministic, right? It's not something we can, I don't know, analytically write down maybe. So the planner should somewhat be able to afford this kind of requirements. I mean, I don't know, not every planner does that, right? So some of them just wants to be able to pick up, and some of them accepts task requirements.
Yeah, we were talking earlier about how to take, kind of, there was some particular wording used about like humans don't just grab objects and then do nothing with them, right? You're always doing it for a purpose. So how to add in that additional layer of evaluation.
It's an interesting question where that should be coming from. Should there was an intention to grasp in a particular grasp pose, which might be functionally related to the next task. Right. And I think what you are addressing is, did you achieve that grasp pose with enough confidence? Except confidence is then relative to the next task, to be quite honest. It's a little bit more tricky, but you open a can of worms, which may never end.
Certainly, but
Could you manipulate the ones that you open?
you open the can of worms. That's great. All right, well, let's thank our speaker.